And okay, so back to a few more basics about the class. I think we mentioned it in just a minute. Yeah, with our syllabus highlights. We talked about all the portions of the class. We do have a lot of what we call tests, and that's kind of a scary word maybe for students. We have a lot of tests. There are 6 test-like activities in this course, on paper, written. And what those look like is we have weekly homework, and then every couple weeks, we have a test, which will take the entire class period. It'll be on paper. You have nothing but calculator, something to write with, and a ruler. We have a lot of graphical interpretation in this class. So we drawing timing diagrams, and we want to straight lines and right angles, all that good stuff, like you're in a drafting class. So we are going to have a lot of tests in this course that we will, for many of them, reflect on in following classes. So we'll take the test. It'll be graded. We'll go through the test in its entirety. So we'll all take it on paper. I'll get everything graded and we'll send it back. So there are 1, 2, and then the midterm, and then 4, 5, and then the final. So 6 total. 1, 2, 3. 3 is the midterm. 4, 5, and 6 is the final. So midterm and final are slightly longer, and the stakes will be slightly higher. The other ones that are distributed throughout the semester are really intended to be a learning tool. And so we will take them as a test, and then we'll kind of look back over them, reflect on them, make sure we're getting what we need from those. They're highly based on the homeworks as well. So keeping up with your homework, which is tied to the course topics, is how you succeed in those areas. That might be all I had about the general stuff of the course. On Brightspace, you can go to your grade book. Everything's in there. 100% of the points are listed. And so as we do things, you can see your grade book fill out. We don't have any weights or anything associated with this class. It's just strict points. So you can see how everything's distributed on there and see how you're doing in the class. And obviously connect with me if you have any questions or concerns as we go. That's kind of the general idea, though. Lecture and lab, homework every week with tests intermittently. That's kind of where we're headed. For now, you'll see it as we go as well. Any questions about the general format this class is going to take? We'll pass out lab kits later. I'll mention that as well. So, feeling pretty good here? Feeling pretty good there? All right, excellent. So back to where I was. Week 1, digital systems, series parallel. We're basically going to just kick off what the idea of this course is. As a fundamental building block, we need to establish just the circuit definition of a 1 or a 0 to kind of kick off what we're talking about. And then we're going to build more and more electronics on top of that. A little bit about series and parallel. So some terminology, some background. We'll introduce a few more things as we go. Who's ever heard of a Rube Goldberg machine? Is that familiar? So what is it? Who wants to tell me what that is?
An extremely complicated machine to achieve something simple.
Yeah, extremely complicated machine to do something simple, typically in a high number of steps, right? So in our figure here, we have a pendulum knocking this truck that's rolling down a hill. It's got a needle, I guess, and hitting a water balloon, filling a bucket, pushes that down, knocks over the dominoes, right? A many-stage process to ultimately maybe just, press a button over here, for example. A Rube Goldberg machine is a mechanical equivalent to the type of systems we're going to set up in this class. And what I mean with that is we will examine and define the building blocks for setting up individual logic gates or an individual adder to add 1 bit to 1 bit. And how do we combine those together? And then we're going to expand the things we can do by scaling up that functionality. So if we can add 1 bit plus 1 bit and get some result that's a 1 or a 0, we can now add 2 bits and 2 bits just by having 2 of that circuit, or 4 bits and 4 bits. And then if you scale and scale and scale, you can then have 32 bits plus 32 bits, right? Which would be an integer plus an integer. And so we have to build out from nothing or from very little, like your electronic components, resistors, and so forth, up to where we can interface with software effectively. And so we're filling in that space with this class. How those actions happen are through charging and discharging of the components, and from voltages being present or not present, and transistors being on or off. And so if we look to maybe think of the C code line X equals 3. Well, we need the number 3 in existence to be moved over to a register. We have clock cycles driving that action. We have movement of bits one at a time, or potentially in blocks of 8. There are many stages that are going to be tied together to do a simple action. So electrically, the concept is similar to the idea of a Rube Goldberg machine. And we're going to build up small pieces and just keep building forward until we can do complex things like send data over a communication serial port, for example. But we need to define all the components, connect them all together in a very specific way, and we'll see how we can make that work. So we're building out basically what is already embedded in a lot of microcontroller, hardware you would buy from Arduino, for example. All right. Typically, I show this in the form of there's a music video that plays through a Rube Goldberg machine. Go watch that on your own. I don't know how that goes over the channel, but I'll just leave it at that. Concurrent is not a word I ever used before I was teaching this course, but existing, happening, or done at the same time. And what is implied by calling this class concurrent digital systems is it is not sequential, like C code. C code executes one line, and then the next line, and then the next line. This class and the electronics we're going to define is more similar to if you drop a ball onto a ramp and it maybe bounces and then rolls down. We're not in control sequentially of those actions. They happen because of the physical setup. So if I set a ball on a ramp and let it go and it rolls down, maybe goes around a loop if you got a setup with a track. Those actions happen because of the physical setup. It's not a sequential initiation of those actions. And so when we talk about concurrent digital systems, we're talking about systems that are driven by a continuous clock signal that happen due to flags, to registers, which a 1 or 0 bit being energized or not energized. The state of the circuit is what drives the action, not sequentially running C code. And so that's the big difference in our lab setup as well. The FPGA is a circuit. It's not a sequentially running piece of C software. So there are some key differences in what we are building and how it's working. And you may even remember from your earlier interfacing, with buttons and stuff in 179, maybe your code, if you didn't program it to check the button enough, you miss a button press or it skips something. That is not a concurrent design, but something like the front panel of a microwave where you're looking for presses of the buttons would work better to have an embedded piece of circuitry that reacts immediately and always is in effect because it exists, rather than looking at sequential logic where you're maybe moving through and you have a short window in a loop where you're trying to catch a button press. So concurrent is the key point of this class. We're making electronics that happen because of what they are. It's not sequential C code. All right, we talked about all the syllabus stuff. Go ahead and look at the syllabus on Brightspace if you have any questions or concerns. Most of it I've said already, and just check in with me if you have issues. So one thing I wanted to just leave with in this first motivation, if we had an Arduino Mega, which I know we've used here at New Albany, and I'm pretty sure you've used at Kokomo as well, in some of your classes, how would you run 256 channels of PWM from an Arduino Mega? Exactly, you cannot. There is maybe 5 or 6 channels of PWM at most, limited by your onboard timers. As a sequential logic-based operation, that is simply not possible. But if you have the circuitry to run one PWM channel physically, and in analog style, rather than having a program sequence, you can just copy that 256 times. And so, FPGA, which is what our labs platform will be on, can do things like run 256 channels of lights at once. You can scale with concurrent designs in a way that you cannot with code. Now, we're limited in some other ways, which we'll kind of look at the pros and cons as we go. But scalability is a lot of the realm that we're in. And when I talk about scale, a lot of students do have in their mind the idea of scale with computer processors and memory, things like that, RAM memory. If you have an 8 gigabyte stick of memory, that's just 1 gigabyte worth of transistors copied 8 times. Well, 1 gigabyte is just, 1 byte copied over 1 million times, right? So scaling by multiplication is a really key element of how we can expand our capabilities here. And I mentioned that with the adding numbers together earlier as well. And speaking of numbers, this is, we're not going into great detail on number systems, but I did want to mention it. We're familiar already with the idea of binary number systems, most likely. It's embedded into a few course versions here, and I'm sure you all have encountered it in your 179, stuff like that. So we'll be working with 8-digit binary in some instances. Actually, for a lot of our work here, we just start with a 1 or a 0. But as we expand and multiply, we'll start looking at things really in chunks of hex, so chunks of 8-bit numbers. So just refreshing, your binary will happen during the course of setting up our homework, things like that. We won't be going into octal, but we will use decimal, binary, and hex kind of frequently as we go. So just keep those items in mind. And remember that the name indicates the base of that number, decimal being 10, binary being 2, hex being 16. So we'll be using decimal for many things. We'll be looking at binary frequently as we build out smaller chunks of logic. And then once we kind of expand beyond what we can do on paper, hex will be how we kind of address a specific place in an 8 gigabyte memory chip, for example. We'll look at strings of hex that allow us to interact with that and connect up to kind of where we take off with C programming. So a few layers to that. So we'll start at binary and circuits at the base level, kind of build up to hex and how it interfaces with programming. Although I should say, this is not a programming class. It is really an electronic circuitry course. A couple quick conversions. You all remember this stuff. You can go decimal to binary. That's the hardest part. I'm sure you all can do that personally, but so can the little search bar on Google, right? So double check yourself if you have any concerns, but just make sure you're comfortable working with different numbers. Decimal to hex, similarly, but hex to binary is what we use most frequently. Remember, 4 digits of binary goes to 1 digit in hex, the 0 through F table. Make sure you're comfortable in that space. We will talk later on about more human interface type things, and binary coded decimal comes into place a lot with that. Binary coded decimal, as you probably have encountered or remember, means using 4 bits to encode 0 through 9. We're not using the letters, we're just showing numbers encoded in binary. So if you want the decimal number 12 in BCD, that's 0001 and then 0010. So each digit gets its own 4-bit number as part of that. Did I say hand up there? Is that just stretch?
No, that was.
All right, it's all good. Okay, ASCII, we've all heard of ASCII, right? We remember our ASCII. We didn't lose it over the summer, left it at the beach somewhere. Remember ASCII? All right, a couple nods here. All right. So when we're talking about ASCII, that's a dreadful slide. We are talking about representing characters with 7 or 8-bit strings, and how we assign that is not through a numerical calculation, but through a table. And so this is an example of an ASCII table. It's dense and not friendly on the eyes. There are other versions, but essentially you have what's represented in hex, an 8-bit number, will have some equivalent character. So when you press a number on your keyboard, that gets converted to ASCII, sent to the computer, and then translated back if you use that or output that somewhere. So when we lean more into interfacing with humans, human people, BCD comes up because we're looking at individual digits, not letters. And ASCII comes up because we're looking at interfacing with text or keyboards, which is not natively understood by computers, but it's critical for the human user to be able to understand. So ASCII will come up later as well. Just wanted to throw that slide in there in case you need a refresher. A couple examples here. Hello, the capital H is hex 48. And the way I would do that is to find the capital H here and see the hex equivalent of that. So if we had a serial transmission of a capital H coming out of our system and we caught it on an oscilloscope, we would see the hex sequence 48 appear in ones and zeros on the scope. So we're talking about 8-bit binary strings or hex equivalents. Okay, ASCII versus binary. Binary is a number. It's numerically linked to its ones and zero and its base amount. ASCII is a lookup table, so it requires a translation that's not purely a calculation. All right. Again, just filling in more definitions, shake off the dust from summer and whatnot. Clock waveforms will be key in driving a lot of the action. Do you guys remember interfacing or using a clock in the past? Where was that? Where do we have a clock signal that we used?
What? Yeah, Belgium. What they call?
179, what was our clock?
Didn't we do it to where it was like 1 minute adds to 1 hour?
It was, yeah, we didn't directly interface with it. It drove the action, but we did reference that 16 megahertz clock on a lot of our earlier boards we were working with. But the way it was used directly was pretty far under the scenes. We did directly use it when we talked about timers, because we had a prescaler where we could divide down that 16 megahertz and get slower ticks of our clock. That was one instance of interfacing with the clock, but we're going to be using clocks in a lot more dynamic ways in this class. So I just wanted to highlight, you guys know this stuff already, you might know it without even about period and frequency or reciprocals of each other. We'll be talking about period and frequency a lot because we're going to be talking about clock waveform timings a lot. And the reason why we do that is the scale that we are at in this class is the scale of nanoseconds. So like the amount of time it takes for a transistor to charge up and turn on and then turn back off. We'll be looking at the speed that electrons propagating and talk about processing at gigahertz speeds. And what's our engineering notation for gigahertz? 10 to the, yeah, 10 to the 9th for giga, right? Is that right? Yeah, mega is 6, giga is 9. Yeah. So anyway, fast. So 1 over 10 to the 9, we're talking about periods that are quite small, like in the nanosecond. So you're going to be at kind of extreme ends of that when we look at period versus frequency. Also, we're going to be doing a lot of analysis that is not intuitive to us as humans because we don't feel really nanoseconds of time or see things happening in gigahertz. And so a lot of what we do will be highly zoomed in, looking at timing diagrams that capture 20 nanoseconds of action, very, very zoomed in. And in some of your future classes, like your 279, you'll actually capture some of that kind of stuff on oscilloscopes and kind of view it physically, but we need to lay some groundwork before we get there. So a couple examples, period and frequency. Make sure you know how to use your powers of 10 so you don't mess that up. Unintentionally, we'll be working with powers of 10 frequently, looking at period versus frequency. Okay. Serial versus parallel representation. We have maybe mentioned this kind of peripherally. Serial being a single stream of ones and zeros. And I thought I had a better figure than that, but okay, that's okay. Serial being a single stream of ones and zeros, and parallel being multiple bits at once. So picture like 8 wires side by side, for example. USB is a form of serial, for example. It's pretty commonly used. Serial has a lot of advantage in that you don't need as much hardware, right? One wire transmits a 1 and 0, and there are some other wires for power, but not as many as required for a certain number of bits in parallel. And so serial transmission is taken over in a lot of cases because we can do a lot more with software encoding that's more economically viable than making multiple routes of data channels, except for the very highest speed applications, like your computer processor connected to the other peripherals on the motherboard is going to be in parallel for the absolute maximum, data transfer speeds. So a timing diagram of a serial representation is something you see here. We have clock signal being shown. We have some serial bits being shown. But really, this is just showing bits over time. You all are very familiar with using oscilloscopes, and you're going to have time on the x-axis when you turn it on at least, and then voltage on the y-axis. Most times we will just talk about 1 or 0. Later in the course, we do dive into logic families that operate at different voltage ranges. So we'll start at 0 or 5 volts, but we'll also talk about some other ranges and hardware mechanisms that use them, or hardware setups that will utilize those. But fundamentally, for a lot of the theoretical structure of how computation is going to work, 1 and 0 will be our notation for talking about highs and lows. Okay, we already talked about parallel a bit, and useful in some specialized cases. All right, let's talk about switches. And before I talk about switches, I will mention today is going to be all lecture. I may even do a little bit extra to give us a bit more flexibility as we figure out the first lab time. So today, we'll just keep cruising. Any questions or concerns, comments about the class at the moment? Or keep on going. All right. I see a lot of happy faces. I see 9 happy faces. Actually 8, one's cut off, but I suspect we have 9 happy faces. So let's talk about switches in electronic circuits. Both manual switches and electromechanical relays are mechanically driven devices. Typically, we see this type of on-off switch schematic view. And this implies a mechanical element such as a push button that we are physically moving. And there are some downsides to that, in terms of wear and tear. And we'll come to that in a minute. But ideally, what we're looking for is a 0 ohm connection when it's on or connected, or closed is another piece of that terminology. And then an infinite resistance when it's off. Switches can be used to create voltage level logic, so a 0 volt or a 5 volt. We've seen this in our interaction with things like pull-up resistors and push buttons, so we can have a grounded, maybe going to an input of our microcontroller, and then when we push the button, it goes in the opposite direction. And here you can see some switches being used for that purpose. We've got ground or 5 volt, just hard connections going to some output. Mechanical switches are great at very simple, small scales, but they do obviously have the drawbacks of having a lot of physical requirement. There's movement involved and there's physical wear down of that kind of thing. If you go track down an MET colleague of yours, they'll tell you that you're going to have friction involved and kind of wear out of those components over time. Electromechanical, well, one last note about this is when we have a switch like this style of switch, what is also required to get a 0 or a 1 out of that kind of switch? So we require some kind of external voltage. We require some kind of movement to happen. What else is required?
Something to read the signal.
Something to read the signal, true. What else is required to get a 1 or a 0 out of this system?
Some sort of load?
Some kind of load, maybe. How about the switch itself? What else is required to get a 1 or 0 out of that system? Or change from what? A way to move it, an operator of some form, or requiring some kind of mechanical interaction to get our signal out of that. If you go boot up your computer and you want to open Word or Excel, do you reach into the box of your PC and start toggling around some buttons? Absolutely not, right? We need a way to interact with switches electronically. And so that's where we're headed is physical switches are great for interacting with people at some kind of small scale. But when you have more and more and more buttons and switches, some electronic interaction begins to be required. And at the core of what this class is going to need is an electronic switching mechanism known as a transistor, and you'll talk about that in a lot more depth in other courses. We're almost there. We just want to mention relays a bit. Electromechanical relays work with coils and contacts. These will be if you do want a mechanical connection to be made or broken or isolated from your digital electronics. We can have some electronics here being driven by a coil. This coil will run current. And what happens when we run current through a coil?
Magnets.
Yeah, we create magnetism. And so depending on the setup of your mechanical switch, it can be normally closed or normally opened. You create magnetism, pull down that lever, and you can open a contact or close a contact. So for electrically isolated systems, relays are very useful in that case because you can drive them electronically, but you still have that mechanical isolation between the two, or electrical isolation. You're isolating the electrical part through that mechanical separation. And relays are still commonly used in a number of instances, but they are driven electronically. And a relay can be used as a switch, but since they are kind of a larger scale and require physical movement, from the perspective of an electron, physical movement is slow. It's way too slow for what we're trying to do inside a processing system. And so you also have relatively high current required to do something like create the magnetism that's going to run a relay. And so it's needed where it's needed. There's no doubt about that. Larger industrial type settings still use relays, of course, to isolate motors and things from your more valuable or lower power electronics. But what we're going to be headed is moving towards a faster mechanism for switching electronically without any mechanical interaction. We have one last slide here just showing our relays in schematic form. So typically we have our coil here that we're going to be energizing. We have our relay contacts here that'll be normally open or normally closed. And so kind of a linked condition here, whether these contacts are closed and then energized will change the state of the relay. And again, we mentioned normally open and normally closed configuration, which is really a mechanical setup of those relays. But we have schematic forms of those. Remember the slash through the relays telling us that we have that normally closed operation versus normally open. Okay, and so relays can produce ones and zeros. Here's some timing diagram. This clock signal is being used to drive a relay. This relay output is 5 volts, meaning that the connection is made. Then when that clock signal is hit, the connection is broken. So the connection is made again with no clock signal, and then broken again when there is. And so the question on the screen is it normally open or normally closed? If it's when activated by the clock, we lose the connection.
Normally closed.
Yes, normally closed. So it sits in a closed state and then opens upon activation. It is what's being shown here. And so we have kind of an output operation opposite of our clock signal. Okay, but still had moving parts. We want to get rid of moving parts. This is an ECET class. Save the MET business for the other folks across the way there, right? We don't want to mix. Maybe we do. Not right now, though. Let's talk about diodes. You have all heard of diodes. You love diodes. You're excited about diodes. What is a diode? Kind of like a one-way current valve of sorts. It allows, outside of breakdown conditions, current to flow in one direction, and stops current from flowing in the other direction. So if it's connected in reverse, it does not allow that current to flow. Exactly. So we can exploit diodes to create logic. And if you think back to your C programming class or your 179, we used logic on occasion. And what I mean by logic is the idea of and or type operations. So if we had, we use this with like if-else statements, for example. We would say if this variable was this and this variable was this, are they the same thing? Then do some operation, else do something else, right? That's a 1 or 0 calculation when it condenses that expression. And so when we talk about exploiting diodes for logic, we can use diodes to set up circuits to make a logical decision on what an output should be based on multiple inputs. In this particular configuration with A and B can be used. This one happens to be an or condition. If A goes high or B goes high, the output is then going to represent a high 5 volt. That happens because either one that is high will allow current to flow, showing the 5 volts passing through, and then it drops completely over this 1K resistor. If the other, one or the other, both do that effect, if both are on, we still have that same effect. It's at 5 volts. That node is all at the same voltage. So with this particular configuration, we can say A or B give us a high output. And that allows us to, with nothing but circuitry, do a selection on, if one or the other thing is activated. As we move through this course, we're going to build out and define a few logic gates. We have a kind of a core 7 logic gates we work with. And then from those logic gates, we're going to build up into adders and multiplexers and encoders, and even processors and RAM memory and shift registers. All of the basics that we had on our microcontroller boards fundamentally can be built up from something like a logic gate. You can see one gate here, but if you're adding 2 integers together, you need thousands of logic gates. But that's the scaling multiplication allows us to make those things. But as we define our logic gates, which we'll do here in just a few moments, each one is going to have really 3 particular components we care about. For this class, there will be a logic symbol, a schematic symbol, and I've got a summary of those coming up in a minute. So this is the schematic for OR, what it's going to look like, but we'll show them all in a minute again. Each schematic is going to have a piece of what we call Boolean logic. Boolean means working with ones and zeros, so and or. And so the VOUT being A, we'll talk in more detail later, but the plus for us is going to mean or. So we have that Boolean logic, so we care about the symbol. We care about the Boolean logic. And then we care about the truth table as well. So we have A and B, we have our VOUT. If A or B are high, we have that VOUT. All right, and we can do the same thing with a slightly different configuration to get an AND type operation, where if A and B are both activated, then we have VOUT going low. We have VOUT going high. But if one or the other is low, you're going to have the voltage drop here over that 1K and then 0 volts left here because it'll be going to either ground on this side. So with slight kind of flip of those diodes and change of the voltage source, we can now make an AND operation. For the purposes of this course, and you're going to hear this many times, the multiplication is our AND symbol. So we have plus is our or, multiplication is our and. We have a whole day lecture on Boolean algebra, don't you worry. We'll do plenty of algebra for your taste. You're going to love it. So we have a a symbol, we have an equation, and we have a logic table as well. Note that this table has the 5s for 5 volts. That's not going to be our typical way that we look at that. We're going to look primarily with 1s and 0s. 5 volts being 1, 0 volts being 0. And here's our AND logic symbol up at the top here. One thing to note, though, is we're making these out of a bunch of diodes. In 2025, we are not making the latest Intel processor out of purely diodes. We're using transistors. And one form of transistor, and this is not the style of a PC CPU, but we can replace some of the diode operation with transistor switching to get the same logic output. And that allows us to more efficiently make those circuitry with less different components. So not, all those diodes and stuff. For microprocessors, later we'll talk about logic families. These are a transistor to transistor style logic. What's in your PC is going to be a MOSFET based logic, so C and N or P and N type MOSFETs, which is a different type of transistor. We'll dig into that a little bit more later. For now, the main idea is we're facilitating a lot of this logic with transistors at the core of the circuitry. And again, just a transistor-based circuit shown here. You have some V in. If you apply voltage there, it's going to activate this transistor and short the V out to ground. If it's not activated, there's no connection to ground and V out is left high. And so what that does is your output is always opposite of your input, or it's an inverter. So we can invert just using simple circuitry as well. Historically, all of these type of functions were done with physical chips. And when I say historically, I mean decades plus. Chips have contained a number of logic gates. This is our inverter logic gate here. This triangle with the dot on the end, we'll refer to that as the inversion bubble. And you just have one input to an inverter, it comes out inverted, right? If you had 8 of these in a row, you can invert 8 bits at once. It's like our tilde operation that we had over in C when we flip all our bits from 0 to 1, so forth, or 1 to 0. Complement the bits. Anyway, chip packages that contained a number of these gates were fairly common. This is a graphic of one of those chips, but they, that's about an inch long, 8 pins on each side or 7 pins on each side. And you would breadboard with those to make your logic circuit. So if you wanted to make your Arduino Mega by hand, it would look something like this. With a lot of different chips for each component. In those chips, you have logic gates. However, the technology has moved forward, and in more recent decades, we have FPGAs, or field programmable gate arrays. So essentially, these are big meshes that can be burned or not burned at all the junctions. And by burning or not burning these junctions, connecting or not connecting them in a certain way, you can get the transistor effect out of these FPGAs, and they can be reprogrammed. So you can burn in an AND gate, an OR gate, a piece of logic, add 2 bits together. Then you could reprogram it if you wanted to. So we're now not soldering chips to design all our logic, but we're going to be just designing through software what our logic is, burning it to the chip. It'll be the fastest circuit building you've ever done, because you just hit go and it makes that circuit happen from your conceptual design. But then you have a chip that you can interface through pins around the chip. A lot of peripheral boards have built-on switches and pins. That's a super dark image, probably can't see much, but we're going to have a similar FPGA, although it doesn't have the built-on switches and buttons and peripherals. As part of our this week or next week lab, we're going to build out a button board with 4 buttons, just to allow us to interface a bit with our FPGA, and we'll look at that software as well. That'll probably be next time or the time after. But that's where we're headed. So we're kind of taking a step from the physical chips and moving to a programmed gate array solution.